Yeah, still good morning, everybody. As you know, Amir and I we have been working for a long time with fiber reinforced concrete. And now we want to see what's new, and certainly nanofiber is one of the directions that it seems to be new. So I want to talk about some work we have done with graphene-based nanofiber, although I'm using fiber term more loosely, as you will see. What are graphene-based material? So you start actually with graphite, and if you have a one-dimensional, it's called fullerene. Zero-dimensional is a fullerene. One dimension is carbon nanotube, and carbon nanotube is probably the most used graphene material in a variety of applications, especially in medical and other applications. And if you have graphene, which is a two-dimension, and then normally when you have many graphene nanoplates, so if you exfoliate it and functionalize it, so from GNP you can get graphene oxide, and graphene oxide is what I'm going to talk about. So let's look at the properties. I guess I can, properties of the three materials. So then I have a property, I can use this, is better, all right. Properties of three materials, and you can see that the modulus is of course very high, especially for the CNT and graphene. For graphene we are talking about Young's modulus of 1 terapascal. Graphene oxide has a lower modulus, but for our purpose it's still very high. The same thing applies for electrical and thermal conductivity. And very high conductivity, for example, of CNT, people are using it for developing cement-based sensor. So if you have a small amount of CNT in cement, then they have a very high piezoresistivity. I'm not going to talk about it. One of the issues, when we use conventional fiber, we know that rheology and workability becomes important. It becomes even very important for graphene-based material because they have a huge surface area, and that means they have a high van der Waals force, is very difficult to disperse. So if you do conventional mixing with fiber reinforced concrete then you see you get up into agglomeration. So many years ago we developed a technique which is now actually used quite a bit. So you start with, I don't want to use it. You start with, for example, here, carbon nanotube, and then you use ultrasonication and superplasticization. You need both to have a stable, well-dispersed carbon, in this case, carbon nanotube. And when you use superplasticizer, then you have this functionalization, so the material then becomes, because of this, you have a very good dispersion. And I have shown dispersed carbon nanotube. So what we found out, that when we started it out, we were talking about 1%, 0.5%, no, 0.1% is the best amount, is very well dispersed, and because of the nanoscale, 0.1% could be percolating. So that's what is the amount. So if you see, when you want to see how dispersed they are, because SCM is difficult to see, so for example, a technique using AFM, and I don't know whether you can see it in the left-hand corner, you can see individual carbon nanotube. And we can even calculate the length of the carbon nanotube, and in this case, about 1 micron long, and the diameter is in the nano, so we have a good aspect ratio. So, as I said, I want to talk about GO, or graphene oxide. And so what GO has is this graphene, which has this functionalized with carboxyl and hydroxyl group. And this makes it easier to disperse. So a lot of people are working with geo, which is commercially available, and as I will show you, it's easier to disperse. So it's a two-dimension, so it's whether we call it fiber or not, but it's a more like, and I will show you a scale on a nano scale in the next slide. So if you look, this is again an atomic force microscopy picture. On the left, you can see that the dimension in the 2D are in a micron scale, but thickness is a nanometer. So that is a well-dispersed geo as seen by atomic force. And I thought it would be good to see what other people have done also with geo. Well, when we add this small amount of geo in cement, people find out that it accelerates the hydration. And here, as shown here in the top, without geo in the bottom, so the CSH particle form around geo, so geo acts as the nucleation site, and that means that, as you can see, as in the next slide, you can see the heat of hydration with a 0.05% from isothermic calorimeter. This is also confirmed that the hydration is accelerated nucleation by measuring calcium hydroxide content from the TGA, and you can see that 0% calcium geo, and with 0.1% you have a more calcium hydroxide. That means more cement is hydrated, more calcium silicate hydrate. So that is one. Another very important thing, and this is what distinguishes nanofiber from conventional fiber, that it alters the molecular structure of hydrated product. This is the work done. I don't know that Xianming Shi is in the audience, but I took his work and they did. This is ordinary Portland cement plus geo, and measuring the polymerization of calcium silicate hydrate. And those who are familiar, Q4 is the tetrahedra is 4 long, most polymerized. You never see that in normal Portland cement. And you can see that OPC plus geo has quite a bit of this. So addition of geo increases the polymerization of calcium silicate hydrate. That means that the calcium to silica ratio of CSH is lower. And that means CSH is more stronger and stiffer. For example, Zhongzin Li is in the audience. He has calculated by using molecular dynamic what is the modulus. Lower the calcium to silica ratio, higher is the modulus. So that is the main difference between conventional fiber and nano level. That at nano level, it changes the hydration product, and we will see the of that. So this is, again, I will show our work in a minute. This is at a very low water to cement ratio. This is also work done at Northwestern. And addition of geo, in this case, you can see increases compressive strength. And I will show a little more of that. So what I want to talk about is carbonation. As we know that concrete is a breathing material, and it breathes CO2. Normally we talk about carbonation. So can we, and we know we want to get rid of CO2, so can we increase this CO2 sequestration? And that's what I want to talk about. My interest, as many of you know, I've been working with carbon nanotube and for a long time, and I didn't really think about carbonation. But then I saw this work done at Purdue where they did nano-titanium dioxide, which we know is used because of photocatalytic activity as a self-cleaning material. So what they carbonated. So if you look at it, so here is percentage of nano-titanium dioxide versus compressive strength before and after carbonation. And they found out that addition of 0.05% or 0.1% increased the compressive strength due to carbonation. And they speculated that this is because titanium dioxide reduces the size of calcium hydroxide crystal, and smaller the size, higher the surface, more carbonation. And we had done some work earlier where we showed that GO reduces carbon hydroxide crystal size, as shown here. Look at the left, where from X-ray diffraction you can measure calcium hydroxide crystal size. And when you have GO, the size reduces. So I said, why not see whether GO can increase CO2 sequestration? So this is what the research that we did, I presented, and was just published. So what we did, we started with GO, water, and then shear mixing. It's well dispersed, added it cement, made the specimen, and then cured them with a 12% CO2 concentration at 23 degrees Celsius, and see whether addition of GO sequesters more CO2. So we checked the bound water 7-day and 28-day, and it's more or less same whether you have a carbonation or not. But here are the compressive strength plotted here with the carbonated and not. So if you look at start with the left, uncarbonated, when you add GO compressive strength, and we are talking about 0.05% or 0.1%. After carbonation, the compressive strength increase of without GO, plain cement, as well as with GO, but it increases even more. So with GO, you have a carbonated as a higher compressive strength, even without carbonation. So then, I don't know whether we can see it here very well, probably not, but you will see calcium carbonate and CSH well bonded, and the dispersion issue you can see here before addition, GO dispersed before in suspension of GO, well dispersed, and GO plus calcium hydroxide to see, because quite often when we have these nanofibers, they may be well dispersed in water, but when we have in the cement, because of the solution chemistry, it changes. But here we have a good dispersion. So why did graphene oxide addition increase carbonation? And the reason is that because of the carboxyl and hydroxyl group, as you add GO during hydration, the calcium ion gets attached, and of course, as a result, when you have a CO2, you have a more calcium carbonate. This is shown here. Where we have here shown is how much CO2 is absorbed, and you can see to the left is a 7-day, substantially more CO2 is absorbed, as much as 30% more, with 0.05%. So GO, small addition increases compressive strength, whether it's carbonate or not, but more important work during carbonation, it increased 30% more CO2. And I think this is just the beginning of a lot of optimization and everything, when to carbonate it, and a lot of other things, but it's certainly very important. And as I mentioned earlier, that GO increases polymerization also. This is FTIR result. You can see there is a more calcium carbonate to the top, and there is a shift in the silica-oxygen bond indicating higher polymerization. So In conclusion, I think that CO2 curing, and earlier people had mentioned different way of adding CO2, but addition of small amount of GO as much as 30%, and I think we could even increase more CO2 absorbed, and then there are other benefits in mechanical and other properties. So I think I will conclude my talk in time.